Assalamualaikum Dr. Nizam, sihat? Dr. Nizam?
Alhamdulillah sihat.
Sihat So I think we have to start because if not we cannot finish by 4:40 p.m. Okay, because the time is very constrained. So Assalamualaikum warahmatullahi wabarakatuh. A very good day to everyone. Okay. I hope everyone can hear me. Everyone? Is anyone
Yes.
cannot hear me? Everyone can hear me. Okay, very good, very good. Okay. So I'm Dr. Iskandar, the chairman of this session. I'm also the deputy chairman of this conference. First, I would like to express my very big thanks to all of you for supporting us in this conference. Okay, so thank you. So thank you very much for contributing to this conference. Okay. I would like to remind that this session is recorded. Okay, and for this session we will have 8 presenters. The good news for the presenters, you will have 2 certificates. One is certificate for presenting, which only your name will be there. Then another certificate is the certificate of authorship of the paper. So to who does not present, you also will have the certificate because you also contribute to the paper and to the conference. So for the presenter, you will have 2 certificates, but for the authors, you only will have 1 certificate. Okay. For the presentation, you will be delivered only 10 minutes. Okay, the most I will allow is 12 minutes. Okay, I repeat myself. The presentation time is only 10 minutes. Okay, 10 minutes. The most I can allow is 12 minutes. Okay, and then I will allow 2 or 3 questions to be asked. Okay, because if not, we cannot finish by 4:40 p.m. Okay, so that's why I have to rigid with the time. Okay, so for the first paper, we will have the title, Effect of Transition Strip on Aerodynamic Coefficient of Multicon Ring for Low Speed Wind Tunnel Testing. May I know who will present this paper?
Bilal Haider.
Bilal, okay.
Actually, doctor, I need to present the second paper first because it is the initial work. So I would request you that if I can present the experimental analysis, the paper ID number 3, that I need to present first.
Okay, so both paper you will present? Both paper?
Yes, doctor. Yes, doctor.
Okay, so the third presentation is the characterization of ancillary wake of general helicopter. So that I will present.
No, second one, experimental analysis for low speed.
No. I mean the third presentation of this session.
Okay, yeah.
Paper is 3. Your paper is paper 2 and paper 3. Okay.
Yes, prof. Yes,
So
doctor.
you just you will present the paper 3 first and then followed by paper 2. Correct? Okay.
Yes, doctor. Yes.
So the third presentation will be me. Okay, the third presentation will be me. The fourth presentation is on the spectroscope analysis of soybean biodiesel swirl flame. Who will present this paper? Paper 5. Spectroscopic analysis of soybean biodiesel swirl flame. Any representative of this paper? Not yet. Tak ada. Okay, it's okay. So paper 8 is the experimental and numerical study on the vertical flow of Multicon configuration. Who will present this paper? Paper 8. The fifth presenter, experimental and numerical study on the vertical flow of Multicon configuration. So no, tak ada belum lagi. Okay. So the following is amplitude modulation of quasi unimodal cavity tone in a low speed flow. Anyone? Amplitude modulation of quasi unimodal cavity tone in a low speed flow. No one. Okay. The following paper, Aerodynamic characteristic of NACA 0012 is suction and blowing slot at various angle of attack. Any representative? I repeat, paper 22. Aerodynamic characteristic of NACA 0012 is suction and blowing slot of various angle of attack. No, okay. So the last paper, assessment of aerodynamic testing of a civil aircraft in Indonesia, low speed wind tunnel, ILST, using analysis of variance. Tak ada juga. Okay. Assalamualaikum Encik Hei. Sihat? Encik Muhammad Hei? Tak ada. So,
Yes, Alhamdulillah.
Alhamdulillah.
Dr.
Tahu tak?
Iskandar, how are you?
Fine, thank
Okay,
you.
okay.
Thank you.
I was
Thanks
there.
for
Thank you.
supporting us.
No, I'm just listening only here. Okay.
It's okay. It's always it's also support to listen also support. Terima kasih
Thank
Encik
you.
Hei.
Thank you.
Okay,
Thank
thank
you.
you very much. Okay. So without delay, please welcome our first presenter, Mr. Bilal. You may share your slide. Thank you.
Yes, thank. I have already shared. It's okay, doctor. Can you see the slides?
Not yet.
I have shared. Actually, the
Okay, I can
internet
see
speed
now.
is a bit slower because there is some electricity problem here inside UTM. So
Okay, noted.
uh, my topic is experimental analysis for low speed aerodynamic characteristics of Multicon configuration. And my name is Bilal, and I am my supervisors, Prof. Shwami, Dr. Shahabuddin, Prof. Wan Khairuddin, and Dr. Nazri. And I am glad to present my paper in this conference, Alhamdulillah. And these are the contents for my basically first I will introduce the background of my work, then wind tunnel model and experimental setup, and the results and discussions. And finally, I will conclude my results. And basically, there is a brief introduction about the history of the delta wing. Basically, delta wings are a special kind of wings, and for delta wings, because they are so much special because they generate extra lift, which is called the vortex lift. Because ordinary aircraft produce only potential lift, and with the help of delta wings, vortices are generated over the surface of the wing. Those enhance the lift, and that enhancement of lift is called the vortex lift. And basically, delta wing can further be divided into two parts. One is the sharp high sweep delta wings, and other one is the low sweep delta wings. And I am a bit concerned about the low sweep delta wings because we are using this in the VCAPs, and these are more concerned with the low sweep delta wings. But with dealing with the low sweep delta wings, it is highly complex and non-linear flow at high angle of attacks. When the vortices are formed, they are not formed at the leading end. They are formed at some space back from the leading edge, and which makes the flow highly complex and non-linear at high angle of attack. So we have to improve the flow so that the stability derivatives can be more consistent and predictable. Called second configuration. And for second configuration, basically, the flow is highly unsteady. It's highly non-linear, fluctuating, and even the discontinuity in the
Mr. Bilal, I cannot hear you.
Dr. Ish. Dr. Ish,
Yeah?
maybe inside UTM they're having an internet problem.
Yeah, yes, I understand because there's no blackout, correct?
Yes, yes. We wait lah. We give him
Mm.
chance and so on.
Mm.
Feel pity to them.
Because they suddenly lost.
Handphone ayah. Handphone ayah.
Dr. Iskandar, can you hear me?
Of course, boss.
Is it my problem or some technical problem? I cannot hear anyone.
I'm also cannot hear.
Oh, I see.
I
Okay,
think Bilal
Then
problem. I think Mr. Bilal
I see.
problem.
The student is staying inside the
UTM.
asrama.
within campus lah, within staying in
Campus.
campus lah.
But apa blackout je hey. Dalam
Oh, I
UTM
see.
aduh.
Okay. Then the the PC is off lah.
Aduh.
If
Kesian
you use
dia.
uh,
Let me call Bilal. Let me call Bilal.
or maybe ni ada ni kot.
Ada
If the time is
presenter
okay,
dulu
okay
kan.
lah. Normally people will give chance to other presenter lah kalau ada, unless
He's
the
coming
time
back.
is plain lah. Okay.
Sekejap.
I'm calling him.
Okay, so siapa
Okay.
call first verify, kalau tak boleh saya present dulu lah.
Okay.
This is good topic ni.
Hello, Bilal. How are you doing? Are you presenting? We cannot see you at all. Your line lost. Okay, so you hold on first. You try to set up all those. Then Dr. Iskandar and Ibrahim will talk first. Okay. Okay. All right. So you don't have to worry. You take it easy. Okay. Okay. Bye. Assalamualaikum. Dr. Is big problem in there.
Okay.
So we go ahead with next papers.
Okay.
And then
So,
we come back to her
actually
lah.
the next paper also him. So
Ah.
I will proceed with mine.
Okay, you go ahead. Okay.
Okay. Please ask him to stop sharing. Mr. Bilal, can you stop sharing?
Okay, wait. Is it okay now, Prof?
Yes, okay, I think. Can everyone see my slide?
Yes, I can see.
Okay, thank you. Okay. So, Assalamualaikum warahmatullahi wabarakatuh and very good day to everyone. I just note down first the time so that I will not exceed. Okay. So my topic is characterization of unsteady aerodynamic wake for generic helicopter. So the author of this paper is Miss Nur Nabila Muhammad. My ex-master student, myself, Dr. Shabuddin Mat, the chairman of this conference, and Mr. Airi Ali, my current PhD student. It's not moving. So introductions. Okay. Helicopters are one of the many flight machines that have been used worldwide because of its agility. So the main distinct of helicopter, it has very big and long propellers compared to the aircraft, which is the main rotor hub and main rotor blades here, which are rotating at very high speed. Okay. So this main rotor hub rotating at very high speed, causing induced complex behavior of airflow surrounding helicopter. Subsequently, this causes flight issue such as tail shake phenomena. What is the tail shake phenomena? During forward flight, whether it's during cruising, segment cruising, or forward climbing or forward descending, the airflow will hit this big fan, this big propeller. So this will causing a chaotic wake, a very unsteady wake that will hit the tailpipe of the helicopter. This will adversely affecting the overall performance of helicopter, occupant comfort, and also the stability characteristic of the helicopter. So the tail will vibrate, transmitted the vibration to the cockpit, and so this will cause the discomfort to the occupants. Also, due to the highly unsteady weight here, this will degrade the dynamic pressure. So this also subsequently this will degrade the stability characteristic performance of the helicopter, because there is the at this portion of the tail, there is where the vertical tail and also the horizontal tail. So this will degrade the lateral directional mode of the helicopter, and the lateral and directional mode of the control of the helicopter. So that was the issue that also caused problem to the rotorcraft community. So for that, to tackle this problem, various simulation software package have been created and utilized, plus experimental study to study this complex behavior. So one of these experimental work conducted is one of my research project. Okay. Okay. So problem statement of the research work. Rotor hub wake, shake, and that have been known to cause complication in helicopter aerodynamic and stability. Okay. So this one is a current issue facing by rotorcraft community. The objective of this research is to investigate the helicopter rotor hub and unsteady weight characteristic related to the helicopter tail shake phenomena. The scope of the work: design a specific weight rate to capture unsteady weight behavior, prepare setup for simulation and experimental works, calibration of transducers such as Collide dynamic pressure. So Collide dynamic pressure transducer is very expensive. It cost me about 4,000 ringgit each, 4,000 ringgit. So for my weight rates, they have 9, so it costs more about 40,000 ringgit, Malaysian ringgit. So very expensive. Also the hot wire anemometer. And then conduct the simulation and experimental works, and then conduct the static and dynamic analysis. So for the methodology, so this one I just go brief, okay. The selected fuselage model for this research work is a standard ellipsoidal fuselage with the axis ratio of the longitudinal to lateral axis is 4.485. Okay, so the model is selected as there are previous study on this model which providing accessible data for comparison. So that's the reason for my research work and also for my last PhD work, I use this kind of model for the validation purpose and also for the comparison purpose. Okay, so the angle of attack for this research work is selected to be -5 angle of attack decreasing cruising segment, because during forward flight the cruising segment is the longest flight segment. So that's why I choose to be at -5. So during cruising, normally the helicopter will nose down a little bit. Okay. So enclosure was created around the model identical to the that of the UTM wind tunnel intersection. So in this virtual simulation work, so we will set up the wind tunnel intersection size identical to the UTM wind tunnel, to the current UTM wind tunnel intersection, which is 2 meter width times 1.5 meter high. Okay. For the simulation machine, okay, from this graph you can see that it's become grid independence at about 54,000 elements. For that we can proceed with our simulation when the number of cells is more than 54,000. Okay, we use the polyhedral mesh in ANSYS Fluent because from previous study, this cell provide higher accuracy in our results. Okay, so this is the model that we use, ellipsoidal fuselage. Okay, so we can see here that I didn't use complete main rotor blade, but instead I will use the shorter blade. So this one is known as a blood stub configuration. According to the previous study from the Europe waterfront and etc., the culprit of the tail shake problem is the rotor hub weight. So the rotor hub weight is believed to be the major contributor to the tail shake problem. So for that reason, for the tail shake experimental work, investigation, etc., we can use blade stub configuration, which is shorter blade, which is about 1/3 of the actual blade. So for that reason, for my simulation and also for my experimental work, I use a shorter blade. A shorter blade, which is the blood stub, because it's believed that the rotor hub weight is the major contributor to the tail shake problem. For this slide presentation, I only expose only two configuration and the result of two configuration, which is without pylon, and another one is with the rectangular pylon. So sometimes people call it also fairing. So pylon or fairing, okay, same meaning. Okay, so two configuration is for this research work. Okay, so the model was positioned at an angle of -5 angle of attack with respect to the direction of the airflow. So from this diagram here, we can see here, so this is the model. The nose down up at -5 angle of attack. So the wind is coming in this direction. The wind is coming in direction. So this the wake rate consists of 9 Fluent dynamic pressure transducer to capture the dynamic pressure of this wake, rotor hub wake. Okay, from this Fluent we can have the pressure, the velocity, and etc. Okay. So the rotational velocity of the rotor was set at the different values to identify the effect of rotor advance ratio on the wake formations. Wake rate was placed at the rear of the model to determine the wake characteristic in the streamwise and lateral direction. Meaning to say that this one we use the PTS prop traversing system will move laterally and vertically. So we can have a mapping here. I think already about 10 minutes. Okay, so I will go faster. So this one is the test parameter for this one. Now I just only show for the 20 meter per second. So we vary the speed and also the advance ratio. We change automatic directly with this RPM. Okay, so this is the mapping of this test that we have conducted. Okay, so this one the mapping here. So we have the 3 plane, C, B, and A, and also some in lateral direction and also in the lateral, and this one vertical direction, vertical wise, and this one lateral wise. Okay, the point was chosen based on the past literature study where it was indicated that the control surface are located at the range of distance between 6R, R is the main rotor blade radius, to 10R from the main radius. So that's why the point allocation. Several lab view-based programs have been developed for static and dynamic analysis, which is RMS, contour plotting, and power spectral density. Okay. So this is the simulation result at the zero back rotation. So we can see here when the speed increase, the maximum pressure also increase. Okay, so you can see here at the speed 30 meter per second, there's more pressure in gradient here. You can see here it's more rate here compared to this one, and also the finding maximum velocity explained by the model increases as the speed increase. So when the free stream is increases, the maximum velocity also increases. So we can see here, even though the SPN, the free stream velocity or the forward flight is only 20 meter per second, we can have higher velocity at the vicinity of the helicopter flow. So because of the shape of the helicopter, so we can see here at 20 we can have almost at 27.83, and at the 30 meter per second we can have 8 until up to 41.83 meter per second. So that's why it's very complicated here. So now there's some velocity streamline of the airflow around the vicinity of the rotor hub. We can see here that the presence of flow separation downstream of the rotor hub. So we can see here this one something called vortex and very complex flow around here. Variation of the speed here. So this one is result from the experimental result. Okay. So the pressure data was converted into pressure coefficient, which is CP. Rectangular pylon managed to reduce the overall CP distribution compared to the no-pylon configuration. So when we have the pylon that will cover the rotor hub, so we will have a lesser CP distribution. Both configurations have similar trend where the pressure is higher at the top region near the rotor and lower at the bottom region near the fuselage. CP gradually increases as the rotational speed increases. Line 1 experience the highest overall CP distribution followed by line 2 and line 3. Okay, so this one the relation of the RPM 1400, 1400, and 1600. So this the pylon, this pylon for this one for the plan B. So plan B is where? Plan B is here. Plan B is here. Plan B is here. And then this one, line 1, line 2, and line 3. So line 1 is the top one. The top one. Okay. So this is the result. And also this one is the for line 1 and line 2 and line 3. So we can see here, so we can see, we know that the rotation is the clockwise direction. So we can see here that the red one is here at the right side, because the rotation of the blade. So that's why we have more CP here compared to the left side. Okay, so this one it shows the same trend for the all line 1, line 2, and line 3. For the no pylon configuration, also for the rectangular pylon configuration. Okay. So this one show that the flow behind the rotor hub is not symmetry. So that's why it's very complicated. Okay, very complicated. So this one the most part. Actually, this one the most part. The most interesting part of the research to determine the frequency of the rotor hub wake. So from here we can see that we conduct the power spectral density PSD analysis. We can see here that the maximum amplitude of the PSD and RMS occur at 2 omega. Omega is the rotational speed. For example, at the rotational at the 1200 RPM, which is equivalent to 20 Hertz. So it happened, the amplitude happened at the 40, the maximum. This one also we can see the at the 40 Hertz. So when we increase the rotational speed to the 1400 RPM or 23.33, so it shows this trend, the same trend, which is the amplitude maximum happen also at the double of the omega rotational speed, which is about 46 here. And same goes when we increase to the 1600 RPM, which is equivalent to 26.67 Hertz. The maximum amplitude also happen at the 2 omega, which is 42. For this one, is 26, this one 56, 57, something like that. Okay. Okay. So also we can see when we reduction amplitude happen at 2 omega, the wave amplitude was found to be decreased when the rectangular pylon was employed. So we can see here when we employ the rectangular pylon, okay, it's here very hard to see the amplitude decrease at the 2 omega. So subsequently, the result revealed that the frequency of unsteady rotor hub wave happened at 2 omega, which is well agreed with the finding of the past research. So this finding also agreeable with the past researchers. Okay. So this one is the summary of the result that got from this research work. Okay. So at this values of the RPM, so we have reduction of the PSD of the amplitude of the pressure. Okay, and the pressure. So when we have employ the rectangular pylon, we will have the reduction of the wake pressure. Okay. Maximum percentage reduction is 88.04% when the rectangular pylon was used at 1200 RPM compared to the no pylon configuration. The percentage reduction also seems to decrease as the rotational speed increase. So we can see here, when the rotational speed increase, the percentage of the reduction also decrease. So mean that it's more efficient if we fly at lower RPM for this kind of problem. Okay, lastly for my conclusion, okay, just a brief. So you can see here. Okay. So from the simulation work, leading edge of the model explain higher pressure and velocity compared to the trailing edge. The maximum pressure explained by the model increases as the value of the speed increase. And for the experimental work, overall CP distribution increases as the rotational speed increases. Top region near the rotor heart explain a higher pressure compared to lower near the fuselage. Okay, and etc. So the most important that we can see that the deployment of pylon can reduce, okay, the pressure, unsteady pressure at the rotor heart rate. Okay, so for that, because I already exceed my time, okay, I have to stop my presentation. Okay, so any question for my presentation? If there's no question, I will pass to the next presenter.
Congratulations, Dr. Iskandar, for the presentation.
Okay, thank you very much. Is Bilal is already ready?
Yes, I am ready. So I started. Sorry for the connection problem. So I continue my present.
No problem. We understand, no problem. Don't worry.
Experimental analysis for low speed aerodynamic characteristics of multicon UCAF configuration. So this is the content for the presentation. And for the introduction, I am not sure when I was disconnected, so I continue again. Basically, for the delta wing, the vortices are generated over the surface of the wing, which creates additional lift, which is known as the vortex lift. And for traditional configuration, there is only potential lift. So this lift enhancement is done with the vortex formation. And delta wings are of two types. One is the low sweep delta wings, and one is the high sweep delta wings. We are more concerned about the low sweep delta wings, for which are more capable of using in the UCAF configurations. So basically, in the previous studies about the low sweep delta wing, more study has been done on the subconwing configuration, and it was came to know that for the subconwing configuration, multiple vortices are formed over the surface of the wing, which makes the stability uh, highly inconsistent and fluctuating. And as we can see in the same alpha curve in this graph, that the stability is not consistent, as for the first part of the graph is linear, then the non-linear regions come, and highly fluctuations are also there, which makes the subconwing unable to fly. So basically, this is a brief background about how we reach about to the multicon wing configuration, because as I told you earlier, that delta wing configurations are used for this UKF configuration, and delta wing we use the low sweep delta wing, and these were combined to produce a conwing configuration. And subcon has severe stability issues, as I discussed earlier. So unit problem was Second was decided so that the flow topology can be studied in detail, and the flow topology can be improved. And there were some suggestions from Delta Wing that we can improve by using the blunt wing and by increasing the span of the wing. And so we reach up with the multi-con configuration, for which the trailing edge sweep was increased and the wingspan was also increased. and basically this is a brief comparison between the subcon and the multicon wing. As for the multicon wing, only CFD has been done till date, and we can see that the vortices are formed highly complex vortices over the subcon, and while for the same angle of attack for the multicon wing, less vortices are formed, and the CM alpha curve also suggests that consistent and predictable CM alpha is for the multicon wing configuration. And basically the objective of my this paper is to identify the factors that influence flow topology and development of vortices for the clean wing multicon wing configuration. As I have decided to study a clean wing so that we can better investigate the flow topology and the real nature of the wing configuration. And basically wind tunnel model, this is the wind tunnel model which we prepared by the 3D printing, and PLA plus material was used. It is a full span model. These are the aerofoils. There is also a twist near the third aerofoil, and basically the leading edge angle is 53 degrees and the trailing edge angle is 30 degrees, and the other parameters are also in this table. And basically for the experimental setup, we decided to do basically two testing for the clean wing configuration. First, we needed to do the flow visualization. For that, we use the lubricating oil with the TiO2 powder to mix, and so that flow can be visualized and we can qualitatively check the results. And other was the aerodynamic force measurement, lift, drag, and pitching measurement. We needed to measure these. And for the aerodynamic force measurement, we use the chair 3 balance. It is placed under the table, and on the top of the balance, the stud is attached, and stud is in turn attached to the molding on wing configuration, as we can see in the figure. And basically, as the turntable is only capable of doing the yaw motion, so I designed a pitch angle device which I place inside the wing model so that we can manually change the pitch angle for angle of attack from -25 to 40 degrees of angle of attack. So basically, now the results and discussion we can carry on with the flow visualization. These are the basically results from the flow visualization. As we can see clearly, for 5 degrees angle of attack, a small apex vortex is formed near the apex of the wing, and there are some traces of the inner vortices also near the wing leading edge, but no leading edge vortex has been formed up till 5 degrees of angle of attack. And for the 10 degrees angle of attack, we can see the apex vortex, and the inner vortex appears to be inner vortex are not existence at this angle of attack, and a small leading edge vortex is starting to develop, and there is some also sweep back uh, uh, vortex type structure at the near the and we can see for the 15 degrees angle of attack that at 15 degrees angle of attack the leading edge vortex had moved upward toward the leading edge, upward towards the upstream toward the wing apex. And similarly for 20 degrees angle of attack, we can see the leading edge, and we can see at 15 degrees angle of attack there is a shear layer region behind the vortex, which can be suggested at the vortex breakdown. And in the 20 degrees angle of attack, we can see that the shear layer region has increased, and this shear layer, this shear low shear region can be supposed to be the vortex breakdown, because for the low sweep delta wings from the literature, it is we are confident that whenever the vortices are formed at the same time, the breakdowns also occurs on the surface of the wing. So this gives a good picture for the multicon wing configuration, this flow visualization, which we can later do with we can later compare with the aerodynamic coefficient. And basically these are the aerodynamic coefficients which we carried out, and this we did for the Renault number of 0.4 million, 0.45 million, and at the speed of 30 meters per second. This is the lift curve. We can so see that clearly there are two regions in the lift curve. One is region A and the other is the region B. In the region A, the curve is consistent and predictable, while in the region B, there are some fluctuations in the curve. And we have taken 4 to 5 times this data, and this data is consistent. This trend is consistent. And then the region B, there is fluctuations with the clean wing configuration. And similarly for the drag, we can see that non-linear increase in the drag can be related to the flow separation, and non-linearity is centered on the drag coefficient features. And similarly, this is the curve for the pitching moment, and this is the main focus over studies because pitching moment is very sensitive to the flow topology as discussed in the previous literature. As we have been confident from the previous literature review that CM is very sensitive to the flow topology, and in this we can see that CM alpha values become markedly inconsistent, and with the as the angle of attack increases, the CM alpha becomes slightly fluctuating, and basically we can see the CM alpha as this is the CM curve, and for the derivative CM alpha curve we can see that CM alpha increases with angle of attack, and as it is tailless wing configuration, so the stability is always in this direction. And we can see that CM alpha varies drastically from 6 degrees of angle of attack. It drastically increase from the static stable to the static unstable region, and at 6 degrees and at 15 degrees, and we can see at 18 degrees, so it again becomes from statically unstable to stable. So the CM alpha is highly moving from one region to in other region. So we might propose some improvement in the flow by so that the CM alpha is more consistent and predictable by applying some flow control device for the multi-con wing configuration. So this is basically the main conclusion of my conclusion that lift is consistent in the region A, and in the region B, lift is fluctuating. Strong correlation between pitching moment and flow topology is noted. And the variation is the CM alpha highlight a non-linear flow topology. The error bars, as in the previous graphs, also indicate that the unsteadiness and the uncertainties of the flow topologies significantly affect the pitching moment coefficient. Unsteadiness and uncertainties of flow topologies need to be mitigated. So this is the proposal for my next work, that unsteadiness and uncertainties of the flow topologies we need to mitigate so that CM alpha can be more consistent and predictable. So this is my acknowledgement that this is a research was funded by UTM, University Technology Malaysia, and my country back from Pakistan, Higher Education Commission.
Thank you, Mr. Bilal. I open for any Q&A. Maybe only one question because we are running out of time.
Okay, congratulations, Bilal. Okay, so I
Thank
can
you.
see good work there. Okay, so Professor Shohami have spoken this morning. Maybe we will bring your model to NCKU for further testing. We will
Oh,
discuss
mashallah.
later on.
Okay.
Okay, we will
Okay,
discuss
bro.
later.
Okay.
And then the good news for you is 1st September is your turn to do the test.
Wow, that's good. Very.
Okay.
Mashallah.
Okay, go ahead with your second paper.
Okay, bro.
I have a question.
Okay.
Okay, my name is Amalina. Okay, Bilal, I want to ask you one question.
Yes, ma'am.
Why the SACON model, the leading edge swept angle is 53? Why 53?
Because actually we are more concerned about the low. We are using a low sweeping configuration, and this they decided from some literature review that for the SACON they propose 53-degree leading edge, the leading edge sweep you are talking about, I think.
Yes, I know that the leading edge angle is a generic model, right? But why 53? Is there any, you found any literature saying that why 53? I just want to know why 53.
Actually, it is basically a range between 45 and 55 degrees of the leading edge angle. As for the Boeing, previously they used 47, I think, if I am not wrong. And for the, because this is range for the low sweep delta wings, which can be used in the UCAF configurations. So they are basically low Reynolds number configurations for which they have to maintain their angle of attack in between this region, in this between this range 45 to 55 degree. So it can be anything. If we have designed this to 50 or 51, it can also be okay. But we wanted to correlate our work with the previous studies, so that's why they use the 53-degree angle of attack. So we are also using that same angle of attack, same leading edge angle.
Okay, thank you, Mr. Bilal. Can you proceed to your second presentation?
Yes, sure. Doctor, can you, it's okay, can you see the presentation? I can start.
Can.
Yes, I can see.
Okay, the effects of transition strip on aerodynamic coefficients of low sweep delta wing configuration. Previously, I presented for the clean wing configuration. Now I will attach some flow control devices and to improve the flow, inshallah. And basically, this is the same content. And basically, introduction is almost the same as the previous for the lift. We get the vortex lift by the use of the delta wing, and we are more keen to study the low sweep delta wing configurations. And basically, this is a brief background for the studies for the low sweep delta wing, and that earlier part of work from VFE2 model, they move to the second wing configuration. And for the second, as I discussed earlier, also complex multiple vortices are formed, and CM alpha is highly discontinuous and fluctuating, and it is unable to fly that wing configuration. And they proposed a diamond wing configuration. As we can see, this is basically second wing configuration, and they proposed a diamond wing configuration by increasing the span and increasing the trailing edge of that wing configuration. And by changing these two, they saw a more consistent and predictable CM alpha. And after that, they proposed those things to the second wing configuration, and second was uh, modified to Multicon wing configuration. And basically, the objective of the Multicon was to eliminate vertical flow at small and moderate angle, and to experiments of clean wing, as I discussed in the previous, that we have done the experiment and for the clean wing configuration. Now basically we are in to make the CM alpha more consistent and predictable. For that, transition from laminar to turbulent flow is basically a main objective which we want to achieve for these low sweep delta wings and low Reynolds number of configurations. For the, as I discussed earlier, that why transition to turbulent flow we need, because these are low Reynolds number configuration and blunt leading edge for Multicon. We will be using the blunt leading edge for the Multicon wing configuration, and sometimes there are some traces of laminar separation bubbles also formed. So transition basically depends upon the turbulence level of the stem, surface details, is the surface rough or surface smooth, and the Reynolds number which we are using. So how to cause transition? There are specific methods in the literature which we can use to make the flow more turbulent. And basically for that, some boundary layer trip devices are used, and some other flow techniques are also used, as can be seen in this figure and this slide. As passive flow control basically increases turbulence level in the flow. And basically why we are using some passive flow, to increase to give more consistent and predictable CM alpha. And for this, vortex generators can be used. They can be implanted on the surface of the wing configuration as shown in the this figure. And we can use the transition strip, which I am more concerned to use, as we because the aim of the transition strip is that they energizes the boundary layer and prevents flow separation. And wires, tapes, 3D tapes, 2D tapes, grids, and there are variety of transition strips we can use. And basically the aim of using some flow control is that we can delay the onset of vortex separation to high angle of attack. And there could be no flow in the no, and basic design for the transition strip matters, which is the height and the location of the transition strip, which we can discuss later, and which in the results. And basically the aim for this all flow control is to make CM alpha more consistent and predictable by mitigating the unsteadiness in the flow. And basically the objective of my work here is to determine the effect of transition strips on flow topology and aerodynamic derivatives applied near the leading edge. So that will be discussed in the coming slides. So for the model, as I will be using the same model as I use for the clean wing configuration, same model with the 3D printing, and we can use the same model. And with the experimental setup, as I discussed, that we will be using the transition strips. And basically transition from laminar to turbulent layer initiated for transition strip height should be the thickness of the height of the transition strip should be higher than the boundary layer thickness, as the critical thickness calculated from the literature was around 190 microns, and we have to apply the double of this height at least, so that some transition from laminar to turbulent can occur. And as you can see in the figures here, this is basically I am using two configurations for transition strips. One I am using the 2D configurations, and one I will be using the 3D transition strips. And I will study the effect of the 2D. I've studied the effect of 2D and the 3D transition strips. And basically they are applied at the leading edge, as we discussed in the previous literature also. As you can see in this figure, that the transition strips are applied at the leading edge on both upper and lower part for the L arc by L CMAC of 1.1%. It is around, for my case, it is around 4 milli of width of the thick transition strips which I used approximately. And basically this is the experimental setup, and we these models we were put it into the wind tunnel, and this is the figure for the 2D transition strip application, and on the right it is for the 3D application of the transition strip. And for the 3D we use the carborundum grades, and we will have comparison for the clean wing 2D and the 3D wing configuration. And 2D, the height of the basically transition strips was around 500 microns, which we will use, which we have used in our experimentations. And this is the experimental setup as discussed earlier. As previously, for the clean wing, we did analysis for only one speed, and here we will vary the speed, and we will also check the influence of the Reynolds number, as we will use the speed 20 meters per second, 25 meters per second, and 30 meters per second. And basically now we can move on to the results and discussions. Basically for the results and discussions, in this part we will be more concerned about the study about the aerodynamic coefficient. And we can see lift, basically this first graph is for the comparison between free clean wing 2D transition and 3D transition. It is the lift curve at 25 meters per second. And we can see clearly that this green line is for the clean 3D configuration. It is more consistent and predictable, as the stall can also be achieved, and the curve is very smooth, and at around 24 degrees the stall is achieved, and there is no fluctuation in the curve. And for the similarly for the drag coefficient, we can see that above 20 degrees lowest drag for 3D strips. At high angle of attack, the 3D strips, three-dimensional transition strips are predicting low drag. Similarly for the CM alpha, this is the comparison for the CM alpha curve, CM and CM alpha curve. This is the CM pitching moment curve, for which we can see that the free transition is free transition, 2D transition, and the 3D transition at 25 meters per second. And for the 3D transitions, the CM curve look to be more smooth and more consistent, and significant deviations from different transition cases, and there is a significant deviation. So there is a real impact of the strips which we are using, that they are impacting the effectiveness of the multi-con wing configuration. And this we can see that for the I plotted CM alpha pitching moment derivative versus angle of attack. As we can see clearly here, this is the green line for the 3D transition strip, and it is very smooth up till 22 to 24 degrees of angle of attack, while the other two curves, the clean wing configuration and the 2D are fluctuating. So we can suppose that we can justify from these figures that fluctuations for free and 2D transitions are there and smooth and predictable for 3D transition strips. So 3D transition strip, the flow unsteadiness and uncertainties in the flow are mitigated so to produce a smooth curve. And this is basically more in detail about the lift and the pitching moment and the drag curve. As we can see, there are three curves, one for the clean wing configuration, other for the 2D, and the third is for the 3D configuration. As we can see, there is no significant, this is basically the plot for the standard deviation, relative standard deviation. As for the lift curve, it is around 4 to 5%. It is not so much noticeable. And for the this graph is for the drag, and drag it is increasing and keep on increasing up till 25% of the relative standard deviation. The main thing to notice here is for the this basically graph. This graph. This is for the pitching moment.
Mr. Bilal, can you speed up your presentation because it's already 10 minutes?
Okay, I will complete in
yes.
2 minutes. Okay, 2 minutes. And this is for the standard. Basically, we can see that the relative standard deviation is very low for the clean wing configuration. And similarly, we have the influence of the Reynolds number also. We can see that for the clean wing, this side, the left side is for the clean wing, and for the clean wing, the influence is less. And for the transition strip, the influence of Reynolds number is more noticed. Similarly, in the case for the pitching moment, that we can see that the influence of the Reynolds number is for the transition strips. And similarly, for the influence, we plotted also the relative standard deviation. This is for the clean wing, and on the right side, it is for the 3D transition wing configuration. And basically, this is the comparison between the clean wing and a 3D transition strip. And basically, this is the flow correlation for the flow topology, which I discussed earlier, that flow has high correlation with the CM alpha curve. As we can see here, that onset at 5 angle of attack is the onset of vortex flow separation. Tip vortex progresses towards the wing apex when the angle of attack increases, as we can see in these figures. As this I discussed previously also in the previous my presentation. Further progressive of tip vortex towards wing apex. And then we can see that vortex breakdown moves upstream of the MRP. Here we can see at 20 degree, the vortex breakdown has moved upstream of the MRP, which makes it more inconsistent and unpredictable. So the conclusion of my work is basically that 3D transition strips predicts a rather smooth and consistent lift curve, and the stall is predicted at 25 angle of attack, where lift is around 1.01. And the 3D transition strips give lower drag at high angle of attack. And the 3D transition strips predicts, which is the main focus of our work, is that 3D transition strips predicts are more consistent and predictable pitching moment coefficient curve up till angle of attack around 22 to 24 degrees. And the relative standard deviation for lift is 4 to 6 degrees, drag is 5 to 25, and for the pitching moment is 20 to 60 degrees. So hence we can conclude that there is a strong correlation between pitching moment and flow topology, and pitching moment is very sensitive to the flow topology. So my acknowledgement against to the UTM for the agency which funded me for doing this work.
Thank you very much, Mr. Bilal. Maybe he want to ask something?
How do you know?
I can see
Thank
from
you.
your face.
Thank you. This is I'm sorry, I have to ask something very basic question. Just not testing, but I just want to know. Because when you do the testing for highly swept wing, like for delta wing last time, there will be additional lift due to the vortex. That's what I believe, the basic concept. But can you tell from the test, from your test here, roughly what is the percentage of increase in the lift compared to due to the swept wing or due to the vortex flow on in this case, isn't it? Uh, this
Actually, Prof, actually for the high swept delta wings, the lift is more generated as compared to the low sweep delta wings. And there are some specifications, some limitations in which we need to use the low sweep delta wings, as we can use in the UKF configuration for stealth and for other important activities in which we cannot use the high sweep delta wings. And in the low sweep delta wings, low, basically the lift is less as compared with the as compared with the high sweep delta wing. But for this case, as there are multiple vortices formed over the surface of the wing for the low sweep delta wing, so we have to make those vortices stable and predictable, so that the stability is achieved, so that the pitching moment, the flow becomes more consistent and predictable.
yes, from CL curve just now that you show, can you tell roughly, in terms of percentage wise, or how big is the contribution of lift due to the separation, in term percentage, if you can? Because
Uh,
I'm sorry, because my experience of doing this something similar was 35 years ago.
okay.
So, so I'm just wondering with the current technology or current model and everything, what happened?
Actually, that basically for the high sweep delta wing, there is more lift increase. But for this, there is some increment in the lift. It is around, maybe we can say that for the low sweep delta wing, the pitch angle, the stall occurs at around 10 to 15 degrees. But for this, as we have already discussed, that the stall of the wing has been improved up to 22 to 24 degrees of angle of attack. So we have improved the stall angle by with the help of the lift which is generated by the vortices.
Okay, another question on the transition. Sorry, Chairman, I'll ask one more quick question. On the next part, the transition with the transition strip test, does it make any difference if you do the test at say 25? I saw you did just now testing at 25 meter per second, or if you
Yes.
do a higher at higher speed, and why
Yes.
roughly you do at the 25 in this case?
Yes, Prof. I have done. Maybe you don't look on these slides. Basically, I have.
Oh, sorry. Yeah.
Yeah, I have done for different speeds also, and I have for the influence of the Reynolds number. I have also discussed this in the last part of
Oh,
my work.
oh, I see. Okay,
So
okay.
there is a significant impact of the transition speed strips on the Reynolds number on the speed.
Oh, I see. Okay. Sorry. Thank you. Thank you very much, Chairman. And I don't have any other question.
Thank you, Encik He. Captain Kanan, are you going to ask something? Captain Kanan? You can ask if you want, because I can read your chat here. So Mr. Bilal.
Yes.
Okay, so Captain Kanan asked, what is the advantage of aircraft flying at high angle of attack for this delta wing?
Basically, for the landing and for the takeoff and for the maneuverability, high angle of attack, more angle of attack is required, so that the aircraft can maneuver, and for the landing and for the takeoff, it is more convenient, and for the stealth and for these all of these things.
Okay, thank you very much, Mr. Bilal.
Thank you, sir.
Now we are going for the fourth presenter. Okay. Spectroscopic analysis of soybean biodiesel fuel flame. Who will present this paper? I repeat myself. The topic is spectroscopic analysis of soybean biodiesel with flame?
Dr. Is,
Hmm.
that's belong to Dr. Cheong.
Okay, betul. Dr.
He,
Chong and Gua Reng Mong. Betul.
yeah, he asked for to join the session at last session.
That session, eh? Okay.
Mhm.
Okay.
So,
So in that case, we move to the next presenter, experimental and numerical study on the vertical flow of Multicon configuration. Who will present this paper?
Yes, sir. I'm here. It's me, Ibrahim.
Ibrahim Madan. Is that you?
Yes.
Okay, so please, Mr. Vedam, you can start to present now.
Yes, sure, sir.
Thank you.
I'm going to share my slides.
Okay, you can share your slide. Mr. Bilal, can you stop sharing?
Yeah. I cannot share. I have to wait for Bilal.
Okay, no problem.
Yeah.
Mr. Bilal, can you stop sharing? Where is Mr. Bilal? Dr. Shabuddin, can you? Okay, that's good.
Okay. Yeah, I will share now. Okay. Oh my God. Can you see my slides?
Yes, I can see. And no, not more anymore. Just now, yes.
Okay. All right. Now?
Yes, I can see now.
All right. Okay. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. My name is
Waalaikumsalam.
Ibrahim Abdullah. I'm a UTM, University of Technology Malaysia alumni. Currently, I'm doing my PhD at National Cheng Kung University in Taiwan. So basically, I'm going to present about experimental and numerical study on the vertical flow of Multicon configurations. It's basically primarily results on what I have been doing for the past 2
Just 5
years
minutes.
of my PhD. And here I'm going to start with the introduction. Why do we need delta wings? All right, why do we need delta wings? Basically, we need delta wings for a faster aircraft, ability of flying at supersonic speed, improving lift force at high angle of attack, the ability of maneuvering at high angle of attack. Factors that affecting flow topology above delta wings configurations. There are many designs that involved with delta wings, and the most factors that affecting the flow topology or flow structure on these configurations are basically sweep angle, leading edge bluntness, Reynolds number, Mach number, and angle of attack. The objective of this study of this paper is to investigate the flow topology about the multi-con configuration with the modified leading edge profile, namely fully blunt leading edge. The problem statement is an attached flow region is separated at the apex of the wing tip vortices, which leads to a dip in the pitching moment, and that's been noticed in the literature due to the development of two vortex structure. The problem statement for this study is applying blunt leading edge influence the flow topology of a wing in a way that the vortex development leads to a stable flow structure? All right, here I'm going to go through the background of this study. The flow topology above delta wings, basically the vortex is starts at the apex of the wing for the sharp leading edge, and then start to take place farther downstream of the a little bit far away from the apex of the wing for the blunt leading edge. And as we increase the angle of attack, the initial flow suppression, the onset of the flow suppression changes location according to the angle of attack, Mach number, and Reynolds number. All right, here is SACON and Multicon configurations. Basically, Multicon configuration is a modified version of the SACON. As we can see here, that this is the SACON configurations, and here's the Multicon. So the area of the surface of the Multicon being increased comparing to the SACON, and the reason to maximize the lift force and also to give more freedom for the control surfaces to take place. Basically, the profile, the leading edge profile for these configurations are, as mentioned here, sharp at the apex of the wing, and then we go here to be blunt, and then at the wingtip it's going to be sharp. And this leads to a complex flow structure. And then here's a previous study that been conducted by Chateau, flow topology above SACON configurations. As we can see here, at angle of attack of 15, that the vortex take place at the leading edge. And then as we increase the angle of attack, we can see two structure systems that take place above this SACON configurations. And then as we increase further the angle of attack, these two vortices going to merge and to form a very big flow structure above the leading edge. And from here, at the angle of attack of 17, where these two structures are formed, basically cause a dip in the pitching moment. And the reason for this study is I went with the fully blunt leading edge to see if we're going to have one structure of the vortex system. So in that, we can avoid this pitching moment problem. Here's summarized for the issues of the SACON configuration along with the AVT 251, which is Multicon configurations. We can see the differences. Basically, the dimensions are almost the same. The changes is only about the sweep angle here at the trailing edge, and also increasing the area of the surface, where the leading edge profile is remains same for the original work, which is sharp, blunt, sharp. And also we're trying to remove the undesirable pitching moment, increase the maximum lift coefficient, as I already explained, and also to improve the control surfaces to give them more freedom and to be more effective at the rear area of the configuration. Here's a study that been carried out by Nanjia about a Multicon. So far, there is no experimental data on the Multicon. There is only numerical analysis, some papers that have some numerical analysis results. As we can see here, it shows that the behavior of this flow structure is somehow similar to the flow structure on the SACON. What I mean here is we can see these two structure that been developed at angle of attack of 12. And from there, this the dip of pitching moment is not been resolved at this stage. And from there, the idea of changing the whole leading edge profile to be blunt came out. The methodology, first, the Fluent Setup. Basically, this was the drawing of the Multicon configuration, and it's slightly smaller than the model for the experimental. The reason is we're trying to achieve as many mesh cells as we can. because of the computer power that we are at. And here's the dimensions of the model. And basically, we want to use K omega and smart alarms for low speed flying condition, for example, 0.2, which is corresponding to 68 meters per second. And the iteration were maximized at 750 to ensure a convergence of the solution. And talking about the blunt leading edge, these are the aerofoils that been changed. Basically, NACA A64 and NACA A65, these are the original aerofoils that have been used in the paper. The only modified aerofoil was MH61, which is for the inner body. And here's the experimental setup. This is the model for the experimental setup. It's we can see the dimensions is slightly larger than the one for the Fluent Setup for the simulation. And here's the wind tunnel that's been used at the Department of Aeronautics and Astronautics at National Cheng Kung University. It basically can go up to 20 meters per second, and the diameter is 500 millimeter, and the intensity, the turbulence intensity is 0.5%. Results and discussions. The test, the experimental test, and also the numerical analysis were conducted at angle of attack of 10, 20, 10, 15, and 20. We only look at 3 angles of attack. So the flow separation is not initiated near the apex of the wing, apparently due to the bluntness of the leading edge. Also, the onset of the tip vortex at the wingtip is noted from both numerical and experimental results. Further noted that at low angle of attack, the flow field is dominant by a large region of attached flow, which is reduced in size as the angle of attack increased. We can see here from the oil film results that the separation, the flow separation of the flow take place somewhere downstream, not at the apex of the wing. And we have somehow a similar footprint of this numerical analysis being conducted by Fluent. And also here we can see this tip vortex has been noticed in the surface tuft method that's been carried out in the wind tunnel. Furthermore, increasing the angle of attack to 15, we can see here the region at the rear part of this aircraft configuration is being enlarged here, which shows the intensity. As we increase the angle of attack, the intensity of this
Mr. Ibrahim,
tip vortex is being enlarged.
Mr. Ibrahim, can you speed up your presentation because it's already 10 minutes?
All right, sure. All right, sure.
Thank you.
And we can see here, yeah, I'll be finished in 1 minute. All right. So here's the region of this intensity of the wing tip vortex. At angle of attack, the region of this intensity vortex has been moved farther upstream and it's been enlarged, as we can see on in this tuft method here, as well as the footprint of the oil film and also the shear stress results from the simulation. Here's the result of the left and drag coefficients. We have the 2 results for K omega and for smart alarms. We can see here we achieved minimum of 0.8 CL and a maximum of 1. And for the drag coefficient, the minimum of 0.4 and a maximum 0.5. Conclusion, high lift and drag coefficient value are achieved at high angle of attack. At low angle of attack, the attached flow is dominant as well as the indication of the onset of the tip vortex noticed. Further increase in the angle of attack flow separation took place near the wing apex. The numerical simulation results do not have many details such as reattachment lines. Compared to the oil film experiment, improvement to the numerical method is needed to identify clearly the leading edge vortex. I'm talking here about 3D structure of the vortex. For the surface tuft method, at high angle of attack, separation bubbles is noticed taking place near the apex of the wing, where the intensity of this spiral motion increased as the incoming flow increases. Thank you very much for your attention.
Thank you, Mr. Ibrahim. Is
Yeah.
there any question for Mr. Ibrahim? So it seems no question. So thank you very much again to Mr. Ibrahim.
Thank you, sir. Assalamu alaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Now we proceed for the next presentation. Topic: amplitude modulation of quasi-unimobile cavity tone in a low-speed flow. Who will present this
Musalla,
paper?
we can stay here. I am Musalla in my car. I can.
I cannot hear. Who will present this one?
That would be me. I
Mr.
am the
Baron.
presenter. Yeah, yeah.
Okay. So please
Okay.
welcome
can
Mr.
make Madhu.
Baron. Thank you very much.
Thank you, Dr. Iskandar. So
Okay,
let
thank
me
you. Most
share
welcome.
my presentation.
You can share your presentation.
Yeah. So can I confirm that all the audience can see the slides and hear me clearly?
Yes, I can see you
Okay.
and can hear
Right.
you clearly.
Okay, thank you very much. Just to confirm, so have I got 10 minutes or 15 minutes to present so that I can pace
Yeah,
myself?
10 minutes.
10
At the
minutes.
most, I
Okay.
can give 12 minutes. Okay?
Okay,
And the
thank you.
NJD time is 2 minutes.
Right, excellent. Thank you very much. First of all, thank you for this opportunity. I will just use 30 seconds of my time to actually congratulate UTM's Aerolab for the 20th anniversary. So without much ado, I will move on to my presentation. So my presentation is a small study related to cavity flow oscillations. It's about amplitude modulation of a quasi-unimodal cavity tone in a low-speed flow. So I'll just explain what it means. A bit of basic stuff about cavity flows. I mean, cavity flows, I'm sure most all aerodynamics people would have heard of cavity flows. It's a very, very basic shape like flow over a cylinder, but very, very interesting and quite not so simple. The shape is very simple, but the flow physics is not so simple. They have several applications like internal weapons bay, low speed applications like landing gears, again, cargo loads and fuel ports and stuff like that. I mean, even in automobiles, there's lots of cavity flow applications. And depending on the geometry and the flow speed, the nature and the physics can change, of the cavity can change. So these are some of the factors that affect the cavity flows. The primary thing that affects is what is called as the length to depth ratio. So we have the length and the depth of the rectangular cavity. So most of the cavities are kind of simplified to a rectangular shape because that's, I mean, most of the generic cavities that we have are kind of can be approximated to rectangular platform. So we will be dealing only with rectangular cavities. So two main features or parameters that affect the flows are length to depth ratio and the Mach number. Certain other factors also play some role, but these two are the most prominent ones. And depending on the length to depth, they have been classified into open, transitional, closed, and there are intermediate flow types like transitional open, transitional closed. Basically, these divisions are based upon the pressure profile that we get on this cavity flow. So this is the cavity flow, this is called as the front wall, and this is the aft wall. And based on the static pressure distribution that you get on the floor, you can call them as, you get different shapes of them, and you can classify them like this. The one of chief interest is this open cavity flow, where you will see flow oscillations. So let's say you collect the pressure data, the time pressure data, and then you do a Fourier transform or you do a spectral analysis. You can see distinct tones like this. Those are called as cavity tones. And there is a well-established mechanisms as to why these tones are generated. So basically, what happens is at the leading edge, you have some vortical disturbances that convect and they hit or impinge the downstream aft wall. And then you get some acoustic disturbance or pressure disturbance that transport or that propagate upstream. And then again, actually, it triggers further vertical disturbances. So it continues in a feedback cycle basically. And based on this feedback cycle, 2 empirical models have been suggested. One is by Rotor. Rotor is, I think, the second person ever to study cavity flows properly. The first person was Krishnamurti in 1952 or something. So these 2 models are there, and this is the one that is most applicable for incompressible flows, low-speed flows. So this is the pressure spectra, the frequency spectra of a cavity flow on a high-speed flow. So one characteristic thing that you can notice from the spectra is that there are multiple modes of oscillation. Okay, so this is the first mode of oscillation. So all these peaks or these frequencies point to some modes of oscillation. So and most of the situations you will have multiple modes of oscillation. So a unimodal oscillation is where you will have only one dominant frequency of oscillation for the cavity. So that is what is a unimodal cavity tone. So the motivation for this work is based on 2 prior works. So basically these are independent works. So they did a time frequency analysis of the pressure inside the cavity. And when they noticed that the frequencies of these cavity tones, they were all amplitude modulated, means that the amplitude of these frequencies, basically these frequencies, their amplitudes are not constants, they are modulated with respect to time. And they found that these modulations were done by other frequencies. For example, when you look at the amplitude of this frequency, it will be modulated by these 2 other frequencies. So those kind of interactions they noticed, and this one was at a high-speed flow, and this one was at, again, a compressible flow of Mach 0.4. So this research was mainly motivated by the fact that what will happen if you have only a single mode of oscillation. So when you have a single mode of oscillation, it's not affected by other modes. So what will how will the amplitude be modulated if it is a unimodal cavity flow oscillation? And also, if it is modulated, is there going to be any periodicity to those modulations? No? And again, what is quite distinct is these studies are confined to a low speed situation. So this is basically the methodology is experimental. So I'll go through the methodology shortly. So all the experiments were done in a miniature wind tunnel. So this is the embedded cavity with flush mounted microphones. There are 3 microphones. The incoming flow, the free stream flow velocity was 30 meters per second. And these are some of the experimental details. So these are the main results and discussion. So when we did for specific Mach numbers and specific L over Ds, we get this unimodal flow oscillation. Okay, so for the L over D that has been mentioned here, and the Mach number that has been specified here, this is the frequency spectra that we get experimentally. And as you can see, only one particular frequency dominates over others. These other frequencies are not really, they are not even comparable to the amplitude of this one. Okay, so this is a quasi-unimodal. Other modes are present, but then this is the most dominant one. So we want to see how the frequency, how the amplitude of this particular frequency is affected. Again, we compared this frequency value to the theoretical Rotor model, the frequency that is suggested by this particular equation here. And you can see that it is more or less they agree with the Rotor model. So what it tells us is that these flow oscillations are caused by the Rotor feedback mechanism, right? So a bit of background if anyone's interested. So basically the way we get all this spectrum is by doing at the heart of this heart of these procedures is what is called as the Fourier Transform. So this is the Fourier Transform, and this is our time series signal. So what happens is that when you do this integral over the time domain, measurement domain, you will only get a function of f. Okay, this is a definite integral, and all the t will get disappearing. So what we want is the f against t. Okay, so you have to change this is called as the kernel function. So we have to change that into a suitable function, which gives us the variation of this signal with respect to both time as well as frequency. So that's why where this wavelet method comes in. So this kernel function is called as wavelet function. So basically it's compared to this one, this has a definite end and beginning, and then you can see that it is just a packet of energy, or a small, a wavelet is a small, just a part of a wave. So it's not a continuous up and down, so it's just a small packet. So we use that instead of this one, and then we slide this across the time domain. And the advantage is that we will get wherever this, so this will have a specific frequency. And when we slide it, we get the amplitude of that specific frequency at that specific time. So we get the function with respect to both time as well as frequency. So this is the result basically. So you get the time series, okay, you do the wavelet method, and you can see this one basically just gives us an average idea. Okay, so in a measurement time of 10 seconds, basically, this frequency dominates. That's all this particular plot tells us, but it doesn't say at what time this particular specific frequency is active. So when you do the wavelet method, we can see that this specific frequency, it's not active at the beginning, and then it rises to a value, and then it rises to peak values at specific points of time. So this is the variation of the amplitude of that specific mode of oscillation, the frequency of oscillation across time. All right. So this is what we are trying to do, is look at how this amplitude behaves with respect to time. So this is the component of that specific frequency. Okay, so this 344 hertz, this is that component. If you split the whole time series into, expand it into a Fourier series, this is what you will get. So you are taking this specific frequency and looking at the amplitude, okay, and see if it is constant or it is varying. You can see that it is varying with respect to time. You do again do an FFT. So you get a spectrum like this. So what it tells is that the amplitude is affected by events in the flow that are being, that are happening at these particular specific frequencies. Whatever events are happening in the flow between 0 to 30 hertz, those are the events affecting the amplitude of this particular flow oscillations. So we have a cavity with L over D 30 meters per second, which showed a single mode of top oscillation. The frequency corresponded to Rotor model, and the time frequency analysis was done using Wavelet method. And the dominant mode amplitude was found to be highly variable. Again, the amplitude was found to be randomly modulated by multiple frequency components in the range of 1 to 30 hertz, like you can see here. Right. So that's also the pace was a bit fast because I wanted to finish that within the time given to me. But any questions, please kindly ask.
Dr. Varun.
Thank you,
Sorry.
Dr. Varun. Okay. Please, any question if you have?
So, congratulations, Dr. Varun.
Thank you, Dr. Shabuddin. Congratulations to you and your team, to Aero Lab for the second decade. And this is the third decade. You're stepping into the third decade.
Yeah, we are going to third decade that. Nowadays, I cannot go alone. We have to have more collaboration with you, okay, with our surrounding. I will create a group soon.
Sure.
So
It's
for
just that, with the pandemic,
this is not the best time to do a meeting,
absolutely.
but we do online meeting.
Yeah. Otherwise, how frequently we I used to visit the Aero Lab. You know, there's a question, I believe. I can't see
go
the
ahead.
chat. I can't see the chat from this window. Sorry,
from Captain Kanan Perumal, is a Singapore airline pilot. He said, what frequency is measured?
So that's around 344 hertz. So this dominant frequency is about 344 hertz. And this frequency is kind of actually dependent on the length and the length of the cavity as well as the flow velocity. So depending on that, we get the frequency. So if we are to increase the cavity size, it will give us lower frequencies, and vice versa.
Okay, any more last question? Okay, if there is no more, thank you very much.
Okay,
Mr.
thank you
Darren.
very much.
Thank you very
Nice
much.
meeting you all. Thank you for the opportunity.
Okay.
So let me unshare this.
Yes, please stop sharing.
Okay, thank you.
Okay, thank you. Now we move for the next presentation, paper 22, aerodynamic characteristic of NACA 0012 with suction and blowing slot of various angle of attack. Anyone represent this one? This paper? Okay, no. So we go for the next paper 29, assessment on aerodynamic testing of a civil aircraft in Indonesia low speed wind tunnel, ILST, using analysis of variance. Is Bapak Subaigo will present this?
Yes, all right. I can change
Can I?
my
Okay.
time.
Okay. Bapak Subaigo daripada LAGG ya?
Yes, okay.
Daripada
And
Serpong.
now me, the name, yes, okay, yeah.
Saya tahun 1999 pernah pergi ke sana. Ada apa tu training bersama dengan Pak Anton, Pak Sujatin, Pak Andi.
Iya, Pak Andi.
Tapi sudah lama lah, 22 tahun.
Iya, waktu
Terima
itu
kasih
saya
Bapak.
sedang di Jepang. Yes, sebentar ya, saya siapkan ininya, bahan presentasinya.
Okey.
It's my start to share our presentation.
Bapak boleh share sekarang.
Ya,
Bapak boleh share presentation sekarang.
share
Jadi
sekarang,
Dr. Darren
yes.
sudah stop.
Wait a minute, I will. Sorry. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Ladies and gentlemen, I would like to make presentation of my paper with a title, Assessment on Aerodynamic Testing of a Civil Aircraft in Indonesian Low-Speed Wind Tunnel using Analysis of Variance.
Bapak boleh buka kamera Bapak?
Yes.
Possible tak kalau Bapak buka kamera?
Mirror.
Kamera.
Okay, mirror.
Bukan kamera sebab mau lihat wajah Bapak.
Oh, sorry. I worry about my signal, but yes, I want to try.
Kalau tak boleh tak apa. Kalau tak boleh tak apa. Saja je lah. Kalau tak boleh tak apa.
Yeah. Because the limitation of our signal in Indonesia.
Okey. Nanti dia akan kacau internet. Tak apa Bapak. Tak apa. Boleh tutup kamera.
Iya, nanti kalau udah saya buka kalau udah berhasil nanti ya.
Terima kasih Bapak.
Yes, okay. I would continue my presentation. I work at National Laboratory for Aerodynamic, Aeroelastic, and Aeroacoustic Technology as the new name of LIGG, PPT83, Agency for the Assessment and Application of Technology, PPPT. Outline my presentation, start, introduction, test facilities, theory and methodology, test configuration, measurement forces and moments, result and discussion, conclusion. Aerodynamic characteristic measurement of aircraft model in the ELST is a primary step in aircraft development and improvement. And then in aircraft production, the analysis of aircraft aerodynamic performance is critical. So the data from the test result must be the correct result and have a high confidence level. So that measurement aerodynamic characteristic of aircraft model result demonstrated that the measuring methods is accurately and precisely complete by the analysis of variance. Introduction. The design and development stage of an aircraft were carried out based on the testing result on the wind tunnel. Aerodynamic testing airplane model in the wind tunnel and the continuous loop under the freeze of the aircraft prototype can be obtained. And from the several methods of aerodynamic analysis, the process of testing wind tunnel on aircraft model is still believed to be method that are quite effective. Facilities in the ELC, we saw this is the building of the built in 1987 with the configuration diagrammatic like this. I think it is introduced by several authors. And then the specification of the test section 4 meter times 3 meter and the long of the test section is 10 meter. Wind speed of the wind produced by generated by the wind speed up to 100 meter per second. This is type of closed circuit and uncontracted type. Contraction here is 9 to the 1. Facility in the section in the wing strut and central strut. And the top of the test section, we have external balance to measure 3 component forces and 3 component moment. The theory and methodology of ANOVA analysis of variance, we use the F-test in one-way ANOVA. F is ratio between group variance to within group variance. And in the two-way ANOVA, the following information need to interpret the model. The F shows the degrees of freedom for each variable, number of level in the variable, and sum SQ is the sum of square created by the level of the independent variable and the overall means. Mean square shown the mean sum of square. F value of the test statistic from the F test divided by the mean square of the experimental. And the value of the probabilities in the value of the F statistic, and so how likely that the F value calculated from the F test would have occurred in the null hypothesis of no diffusion was true. From this output, we can see that the forces, type, and moments explain a significant amount of variation, and average model yields the value greater than 0.01. The measurement forces and moments in ELSC shown by this figure. The model of type passenger aircraft installed in the test section, supported by the wing strut, and then the force and moment can be measured by external balance at the top of test section, and wind generate speed can be controlled in the test section by the panel here and give to up to 70 meter per second. Also altitude control by this control room if from minus 10 to up to about 18 degrees, and the data will be sent to the PC data processing computer, and then processed by the personal computer for data processing. And test configuration, some of test configuration of the model, we have some configuration like V wing, B mean body, and nasal, G landing gear pairing, V vertical tail, H horizontal tail. But in this study, we just only study on the wing and body configuration. And at the table 3, we have some run, we call by run 9 up to 11 at the speed 70 meter per second. Angle of track varies from minus 10 up to 18. and beta angle side angle is 0. And for the long repeatability means that after some installation and then we return to the first configuration, we call by like run 78 with the speed same with the before 70 meters con angle of the variant angle from -10 to up to 80 degrees and run 80 and run 81. Here are some results for my experiment in the run 09. We have varied alpha from 10 point. Here it's correction by the alpha mechanism. We have angle of attack alpha minus 10.26 up to 20 point. Here is after stall because this is TL maximum and then stall taken 2 degree after stall. And also we find the first measurement from Drake and side force and the moment for CM25 and CO0. And if we use the Excel software and we show the result of one way table for CL, we have 27 data and the sum of the CL, all of that is for the column 1 is 17.815, average mean 0.659 814, and variance is what is. And for column 2, show by this value, also in column 3. And from the ANOVA, we can compute for the F value between group and divide by within group and have the value is very small and the p value around 1 with a critical 3.113. Graphic plot characteristic CL phase alpha. If we have we plot this CL phase alpha shown in the figure 6. On the other hand, the one-way analysis on the variant table of CL can be shown in table 6. According to table 6 of the one-way analysis of variant, the parameter value f is tiny and the value of p is almost 1, indicating that there are no significant variation between run series 01 up to run 11. Table 8 further indicated that if the value of f is large enough and the p value is quite tiny when using the two-way analysis of variance. The order of variation is extremely minimal, ranging from 1.43 10 to the power minus 7 to 3.48 10 to the power minus 4, implying that no differences. And also result of the run 10, we have obtained a variation of CL CDCM 25 TU 0 TU varies to the alpha angle from minus 10.23 up to 20.61, shown by this table. And the result from this calculation for one-way table, we can find that in the ANOVA function f, the value is shown by value 0.001047 and the p value 0.99893. That is the same like the run 09 before. That's in the so table 7. So the one-way analysis of the variant table of curve CL versus CD According to the table 7 of the one-way analysis of variant, the value f is tiny and the value is nearly 1, indicating that there's no significant change between run series run number 9 through run number 11. Furthermore, the table 9 demonstrates that the value f is large enough and p minus value is quite modest. The order of variation is minimal, ranging from 2.33 10 to the power minus 8 to 3.57 10 to the power minus 5, implying that no substantial difference in mean between column and warranted. And also, if we use the two-way table of variance, we have like table 8 here. From row 1, we have 3 data, and some of this is from here is at angle of the minus 10. Average is minus 0.70577. Variance is very small, 4.23 10 to the power minus 7. And if we calculate with Excel, and we can find that the variance is a very small value with the order 10 to the power minus 4 up to 10 to the power minus 7, I think. That's so, I mean, the analysis of variance, so the set of data aerodynamic for CL is modest in the two-way nova. On the other hand, the value of variance is extremely tiny. Inside the parameter f has a large value and P practically very small, implying the wind tunnel test variation between run 9 is inconsequential. And then we have the conclusion. This series of investigation result to the value of two important parameters in the ANOVA. IEF have a value very tiny, and P is almost 1. Is in the assessment by using the one-way ANOVA for aerodynamic CL, CT, CM25, CO, and CL. That means there is some much of the differences between run 9 up to run 11. The assessment variant analysis of one-way and two-way on the aerodynamic characteristic of the ELST wind tunnel test yielded positive result. That is to say, the assessment of ANOVA application on the model of airplane wind tunnel test demonstrated consistency and accuracy in the wind tunnel test on ELST. Yes, thank you very much for your attention.
Thank you very much. Very, very interesting. Is there any question from the audience?
Can I ask Dr. Iskandar?
Yes, welcome.
It's not asking, Dr. Subago.
Yes.
Just to mention that we missed that wind tunnel. Me, Pak Iskandar, Pak Wan Karudin, Pak siapa ya? Satu lagi Pak Nizam. Ya, kami ke sana trainingnya di nama LAGG-nya
yes.
LAGG-nya melekat di hati kami.
Oh.
Jadi kami pergi sananya kurang lebih 3 minggu ya Pak Iskandar. 2 minggu.
Ya cukup lumayan lama.
Jadi pada masa itu Pak Syuhaimi dengan Pak Khair hantar kami ke sana.
Oh iya. Sayangnya waktu itu saya sedang studi di Jepang untuk
di Jepang ya Pak ya.
Iya. Yeah, so I didn't meet you at that time. Yeah, itu belajar.
Inshallah we will see. We will go there after the pandemic. After COVID.
Yes. Yeah.
Amin.
I will menunggu di sini. Yeah.
Okay, no more question from me.
Okay, from others, is any question?
Prof Syahmi mungkin? Prof Pak Khair mungkin?
Is there any question?
Saya tidak ada tidak ada Pak. Just to say hello. Salam kepada semua kawan-kawan yang saya pun banyak belajar di LAGG dulu. Kita tahun 90-an. Masa zaman Pak Anton sendiri sebagai ketua dan Pak Sujatin dan Pak Andi. Saya tak pasti pernah jumpa dengan Pak Subagio. Did I meet you before or not sure? Tidak pasti ya.
Iya, belum waktu itu rasanya mungkin nggak sempat ketemu Pak.
Ya, oke. Oke. Anyway, so sekarang partnya di bagian mana di LGG?
Di LGG masih tetap ini Pak, mengetes model-model pesawat sekarang N219
So
yang
the
sedang.
The head is still Pak siapa nama?
Sekarang Pak Fadilah Hasim.
Fadilah ya.
Yes.
Ya, masa
Sering
during that
kesana
time
dulu.
Pak Fadilah is a very junior engineer during that time.
Iya.
Okay.
Yes, that's right. Iya.
Okay, so I have no question. Sorry, thank you very much.
Okay,
Okay, thank you.
Terima kasih Encik He, terima kasih Bapak Subagio. Thank you, terima kasih. Terima kasih.
You're welcome. Yeah, okay, sama-sama.
Okay. Now we can proceed to the paper 5. Spectroscopic analysis of soybean biodiesel swell flame. Anyone will present this paper?
Yeah, I'm here, Dr. Iskandar.
Okay, Dr. Cheong. Okay, ingat siapa tadi? Okay. Please welcome Dr. Cheong.
Good afternoon to all. I'll be sharing my screen now. I'll be sharing my research on the biodiesel combustions. Okay. I'm Cheong. I'm now working for the ISAE University. So, as we know now that the world nowadays are looking for cleaner energy source to replace the fossil fuel. The biofuel are becoming more important mainly because they can be potentially carbon neutral. Okay? The carbon that released during the combustion can be absorbed again by the plant, okay, for the photosynthesis. So, and also biofuels are usually cleaner and the supply is more sustainable. It is anticipated that the bioenergy will be the use of bioenergy will be increasing. Among many types of biofuel, the biodiesel is one of the promising fuel. Okay, mainly because it has a very close physical property with the diesel and also the A1, such as a certain number, viscosity, value, and also the energy density and also the density. But due to the lower biodiesel energy density, we do not use it in the transportation area. Okay? As compared to the Jet A1 and FT fuel, FT diesel, biodiesel is not qualified yet for the transportation, but we can always use it for the land-based gas turbine for the power generation. Usually, we think that biodiesel is generally cleaner than the fossil diesel. Okay, yeah, it is actually correct in terms of a lower soot emission, but research has found that nitrogen, the toxic emissions such as nitrogen oxide and carbon monoxide from biodiesel might not be lower than the fossil diesel. So there are research still going on to find out what is the actual reason that caused the nitrogen oxide and carbon monoxide emission from biodiesel tends tends to be higher. So this paper, in this research, basically to investigate the flame spectroscopy, to investigate the spectra of the flame of biodiesel. Why do we investigate the spectra of the flame? Because this kind of measurement will give the quantitative data for the combustion intermediate species that can be used to explain why some of the emission tend to be higher. So for experimental setup, my burner, as I use it in the Aero lab before. Here's we have fuel tank. Here's a fuel tank and atomizer, and there are also spectrometer. Spectrometer is basically a what we call instrument to measure the combustion species, the concentration of the combustion species inside the flame. And here we have a swirler. Here a swirler was used to generate the swirl flame. Okay. For my testing condition, the swirl angle was varied from 30 degrees to 60 degrees. This table compare the physical property of the diesel, biodiesel, and natural gas. Okay. As compared to the diesel, this is the diesel flame, this is the biodiesel flame. Yellow part is actually the soot. Okay. So as we see, the biodiesel is cleaner than diesel because there's no the orange flake. So that means there's no soot in biodiesel, but we're actually more interested in nitrogen oxide and also the carbon monoxide. So as compared to when compared with the diesel, the biodiesel tends to produce higher OH radicals, CH radicals, CN radicals, and the C2 radicals as compared to the diesel. Okay. One of the reasons why these combustion species are higher in biodiesel is because biodiesel has longer chain length. The chain length for the biodiesel is longer than the also. Although the soot is not something we want, but the soot in the swirl flame has some of the radicals, and also due to the double bond inside the biodiesel is also one of the reasons that promote the CH radical production. And as we compare the different swirl angle, 30 degrees tends to produce higher swirl intensity as compared to the 45 degree and 60 degree. Because in the swirl flame there is a recirculating flow. Okay. In 30-degree operation, the recirculation is weakened. So this slow down the chemical reaction. So means the more species are stay inside the reaction zone, but it's not consumed. So this one of the reasons that causes more combustion species, higher concentration of combustion species. And the 60 degree tends to produce lower radical, because in 60-degree operations the swirl flame is more intense, so the reaction tends to be faster and most of the radicals are consumed very fast. So it's lower down the density of the radical. So more radical means higher chances of producing the undesirable pollutants. So in conclusion, the flame characteristic of soil biodiesel was compared against diesel, okay, using swirl angle of 30, 45, and 60 degrees. 30 degree swirl angle promotes the formation of these radicals for both diesel and the biodiesel. The radical intensity is reduced when the swirl angle increased to 60 degrees, because faster rate of reaction. So when these radicals are consumed faster, means the tendency to produce undesirable emissions will be lower. So this book shows that the slow angle, as we vary the slow angle, we have the opportunity to, we can actually control the emissions of the biodiesel. So if we would like to lower the emissions of the nitrogen oxide and carbon monoxide in the biodiesel, varying this varying this slow angle can be one of the solutions. So for me.
Thank you very much, Dr. Cheong. I open for any question from the audience.
Oh, no question. So I just would like to say thank you for your contribution to the ISAE, Mr. Dr. Cheong. So, okay, thank you very much.
Any other question from the rest? Okay, if there is no question, thank you very much, Dr. Cheong. Now we move to our last presentation, paper 22, Aerodynamic Characteristic of NACA 0012 with suction and blowing slots at various angles of attack. Is Mr. Ahmad Hussein already?
Inshallah.
Oh, so you are Encik Ahmad Hussein. Okay. So please, you can start to share your presentation. Thank you.
Okay, will do. Thank you. Right. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So I'm Ahmad Hussein from FTTC, Flight Technology and Test Center, School of Mechanical Engineering, UITM. I'm going to present a research title, Aerodynamic Characteristics of NACA 0012 with suction and blowing slots at various angles of attack. So the study of aerodynamics is very broad, but in my study, we are going to focus on the boundary layer controls. Okay. Now, basically, boundary layer controls is used to control the transition and separation delay, and also to increase the lift and to reduce the drag and also to suppress noise. Okay. Basically, there are various approaches to control the boundary layer, but in this particular slide, I'm showing two approaches. Okay, we can be broadly categorized into two approach. The first one is the unpowered high lift systems, and the second one is the powered high lift systems. Okay, so the unpowered one has been used in the commercial flights, for example, in the Boeing and also Airbus. Okay, for example, in Airbus 320, okay, the aircraft use the leading edge device, for example, slat, and also the single slotted flap. And with this incorporation of high lift device, it can increase the maximum CL, okay, up to around 3. Okay, and also, for example, with the Boeing, okay, with the leading edge device, okay, and also with the triple slotted flap, okay, it can also further increase the maximum lift coefficient. But generally, for the unpowered high lift system, okay, the CL max is in the range of 3. To further increase the lift of the aircraft, okay, it is required that we use the powered high lift system. Okay, it can increase up to maximum CL of 7. So the plot on the right shows, okay, the effect of flaps and also the effects of the boundary layer control through the powered system. So in the case of flaps, okay, we see that the flap increases the lift coefficient at all angle of attacks, okay, at the expense of the stall transition. Okay? The stall angle is lower. However, it can increase the maximum CL, okay, and also the slope of the CL is almost the same. With bond delay control, okay, the CL of the pre-stalled condition is almost exactly the same as the control airfoil, but it can increase or delay the separation further at higher angle of attack and thus increases the maximum lift coefficient, CL max. There are two types of bond delay control in general. One is suction and one is blowing. In the suction approach, okay, basically the low energy segment of the bond layer is removed and is being replaced by high energy flow from the upper layer of the flow. While in the blowing, okay, the kinetic energy is added to the boundary layer directly. So this figure shows the suction approach, whereby we have a suction slot on the surface, okay, and the frontal has showed that the suction through the slot could prevent flow separation on the surface of the cylinder. The layer of low energy air near the surface approaching the separation point is removed through the suction slot. Okay, so this results in a much thinner bond layer, as you can see here. Okay, so due to the suction and more vigorous boundary layer that is able to progress further along the surface against the adverse pressure gradient without separation. Now, these are airfoils with three different configurations: the AF1, AF2, and FI156. Okay, so the AF1, AF2 is incorporated with a suction at the slot, the flap. Okay, it is shown in this diagram that the suction near the flap can significantly increase the maximum lift coefficient, okay, and also increases the lift coefficient at all angle of attack as compared to the baseline case without the suction. Okay, since the flap can operate at relatively large deflection angles and the airfoil can operate at relatively high angles of attack without separation, large increases in lift can be obtained. Now, in the case of blowing, okay, basically the conduct effect is used to further enhance the lift coefficient. Okay, so the main idea was to increase the kinetic energy or the energy of the bond layer and thus re-energize the boundary layer. Okay, most application of tangential blowing for flow control exploit the conduct effect, as I mentioned before, the tendency of the fluid jet issuing tangentially onto a curved or angled solid surface to adhere to it. And this is a rather new concept being proposed by Za et al. 2005 called the co-flow jet. Okay, basically they consist of the injection slot near the leading edge and also suction slot near the trailing edge, and there's a microcompressor that controls the pressure difference between the two slots. The advantage of this system, okay, is that it can delay separation, okay, it can increase the lift coefficient of the airfoil and also reduce the drag, and thus increases the stall margin and also low noise. Abhinav et al. 2016 has shown that this CFG concept can improve the base airfoil by 33 to 67%. Okay, and as you can see in the figure, okay, it increases the stall margin, okay, and also it increases the lift coefficient. Now, in the present study, okay, I'm proposing an opposite of CFG. So instead of the suction at the leading edge, instead of the injection at the leading edge, now the injection is at the trailing edge and the suction at the leading edge. Okay, so this is what we proposed. So the suction slot is positioned at 10% of the chord from the leading edge, and the blowing slot is positioned 80% of the chord at the trailing edge. And we chose NACA 0012 as the baseline airfoil. And the depth and the width of the slots are 2.5% and 0.5% of the chord length respectively. So we define the momentum coefficient to define the jet velocity of the slots. Okay, so this is the momentum coefficient, and for this particular case, this formula can be reduced to this one. Okay, basically it's a function of the slot width, the jet velocity, the free stream velocity, and also the chord of the airfoil. In this particular study, the momentum coefficient is varied between 0.025 and 0.05. And it is important to note that in this particular study, so the momentum coefficient of 0.05 indicates that the jet velocity of the slot is equal to the free stream velocity. Okay. Now these are the computational domain. Okay, basically there are three levels of refinement imposed. Okay, the first one is the region based, where we have 4 levels of refinement. We have a surface based refinement with 2 levels and also 6 levels of boundary layer refinements. So it is very crucial in this study that we refine the boundary layer so that we can get a very accurate lift and drag data. The boundary layer refinement is to capture the expected high gradients, and the grid consists of 251,000 elements, out of which 248,000 are the hexahedral elements. And the maximum mesh non-orthogonality is 46.54, and the maximum skewness is 2.49, which is considered good. And we first validate our solver with respect to the wind tunnel data published by NASA TM 4074. And in this comparison, okay, we have CL versus angle of attack plot and CD against angle of attack plot. And we see here the pre-stall condition, the CFD solver, which is open foam, can accurately predict the CL and CD of the airfoil. But beyond the stall, okay, there is some discrepancy of the data, but still the trend is there. So each cases took around 11 to 12 hours using the Core i7 8th generation PC with 32 gig DDR4 RAM, and here we use Pala-Amaras model. Now coming to the results, we have here baseline represented by the circle point and symbols, and the last step here is for leading edge suction, trailing edge blowing. So which means we have 2 slots activated with CMU of 0.05. So we have last step CMU 0.025, and for the last case, which means the blowing part, trailing edge blowing is turned off. It's only leading edge suction is on with CMU of 0.025. We can clearly see here that the modification of the airfoil with less step and less increases the CL max significantly. However, with the less step, with the blowing and the suction, it reduces the lift coefficient in the pre-stall condition. However, it delays the separation much further at higher angle of attack as compared to the less cases. And it is interesting also to note that the slope of the lift curve is almost identical for all cases, regardless of the momentum coefficient imparted on the airfoil. Now, the reason for the increase of the maximum lift coefficient is because of the minimum pressure coefficient at the leading edge. In the last step cases, produce a consistently lower lift coefficient, okay, because of the minimum pressure peak is lower for the last step case as compared to the less, and hence a lower pressure coefficient on the top surface. Okay, the blowing cause separation in the downstream region does increase the surface pressure and reduce lift force, as you can see here. Due to the blowing of the air, there is a flow separation, and this result in a low lift. Despite this shortcoming, the blowing action near the trailing edge of the airfoil has shown to further delay the stall, as can be seen in the previous slide here, where the last case stalled at around 28 degree, and with the last step case stalled around 30 degree. Now, if you look at the stall characteristics, this is the baseline is very benign, very mild, but with the modified case, okay, the stall characteristic is very sharp. So you see here, this is the last step case at 28 degree pre-stall, and this is at 29 degree post-stall. So there is an abrupt change in the flow behavior, and there is a leading edge separation. Okay, we can clearly say that this is a leading edge separation because of a almost uniform pressure coefficient contour surface contour plot here. In terms of drag coefficient, okay, it is surprisingly that this control airfoil, the less and less step, produces negative drag coefficient. Okay, we deduce that the reason for this observation is due to the blowing action produces an opposite force which tends to push the airfoil forward, and also the suction of the stream near the leading edge reduces the local boundary layer thickness and thus reduces the skin friction drag. So hence explaining why we have a negative drag coefficient in the pre-stall condition. Now to conclude, okay, comparing all the cases, the baseline, the less step with 0.025 momentum coefficient, less step CMU 0.05, and also the less cases with CMU 0.025. The last step with the highest momentum coefficient produces the highest stall angle of attack, which is 33 degree. However, the maximum lift coefficient is produced by the last case without the blowing slot activated. But the higher the momentum coefficient, the higher the maximum lift coefficient. So there is a competition between the lift and also the stall margin. And also we conclude that the lift curve slope for all cases are almost identical. I think that's all from me. Thank you.
Thank you very much, Mr. Presenter. Is there any question from the audience?
Was the blowing transverse? Okay, I think there's a question in the chat. The blowing is tangential to the surface. Both the blowing and the suction. Okay, no worries.
Any more question? Okay, if there is no more question, so we complete our session for today. So please everyone to switch on your camera because I want to take photo.
Okay.
Boleh
Alright.
buka semua gambar.
Okay. Then
Please switch on your.
luckily, the two of the former head of lab are joining us today.
Yes, yes.
Sure.
Please.
Where is Prof Wan in the another section and no, in another group.
Prof Niau, can you open your camera? Dr. Nik Ahmad Ridwan. Tak ada lagi. Okay, everyone, please smile.
So how long to smile here? Dr. Iskandar?
Okay, last. Again, last. Last. Okay, smile. Okay, thank you very much. Okay, thank you very much, everyone. So, inshallah, next year we will conduct again this conference. I hope everyone will support us again. We are in a very small community, so we need to complement each other to work together, not competing each other. Okay. Maybe Dr. Prof. Shohaimi or Encik He want have last word to end up this session because you are the otai here.
I don't have much to say actually, but I would like to give a big congratulations to the organizer being successfully organized this first international seminar on aeronautics and energy. Yeah, so I hope that we will see again. By the way, I don't know whether I'm still here or not, but would like to hear more from you all and to hear the success story from your side. Okay. Anyone would like to add? Thank you very much.
Thank you, Dr. Shami. Cik Hei.
I would like to also echo the same thing. Congratulations and well organized event to the aeronautical group of UTM. I'm very particularly very proud of all of you. I'm also very sentimental when it comes to the Aero Lab. After 20 years, I try to come in, as much as possible. Well done to whole team, especially the conference chair. The conference chair is Dr. Shabuddin. Sorry, Azan dah mula start. So, and chairman and everybody, thank you very much.
And thanks
Conference
to
chair,
participant as well.
to the participant as well.
Yeah.
Conference chair is just sending text to this guy and this guy and this guy.
Yes. I mean, when I say all, I mean including all.
Just doing it
Okay.
like a businessman.
Okay, so with that, thank you very much again. So I conclude this session with Surah Wal Asri, and to those non-Muslims with your own prayer. Thank you very much. Bismillahirrahmanirrahim. Wal Asr.
Awesome. Okay,
Okay, thank you
bye-bye.
everyone. Hope to see you
Okay,
again next year.
bye-bye.
Thank
Bye.
you.
Thank you all.
Bye-bye.
Take care.
Bye-bye.
Assalamualaikum.
Okay, see you. I will talk to you, Bilal. Your time to do the testing.
Bye-bye. Let's
Bye.
hope we meet physically. The next year's symposium is a physical
Yeah,
one and not an
Yes, we
online
hope
one.
that we to do that physical.
See you again. Yeah.
See you again,
Bye-bye.
Varum.
Stay safe and
Bye-bye.
take care.
Stay safe.
Don't
Take care.
don't give up with Malaysia, Varum.
Not yet.
Okay.
Bye-bye.
Okay. Bye bye.